Welcome to this introductory webinar on monitoring tropical storms for emergency preparedness. I am Amita Mehta, and we will be conducting this training introducing NASA remote sensing data which are useful for tropical storm monitoring. So we'll start with the overall objectives of the training. As I said, we want to identify remote sensing data and tools which help access this data, and basically the tools and data that are relevant for monitoring tropical storms. That's what the focus of this webinar is. How to monitor conditions before, during, and after a storm using remote sensing data. That's what we will see through this 2-week webinar series. We'll also try to understand how remote sensing data can be used for decision-making activities. So with this overall plan, here is the course outline. Today, we're going to talk about overview of tropical storms and their impacts. So this is mostly talking about which data to use and how to use. And then next week, which is May 10th, we're going to actually do monitoring tropical storm conditions during and after storms. So that is the overall outline. Just a few words about this webinar series. We will have 2 homeworks, one which will be posted today on our website, and there will also be another one at the end of session 2. Here is the website, arset.gsfcnasa.gov, and all the webinars are given here, so you can find homework assignments here. And there are Google form links with the homework where you can go and answer your questions. So there is also a certificate of completion given to everyone who attends both webinars, also completes both homeworks, and deadline is 31st of May. And then after all that, in 2 months after the webinar is over, you will receive a certificate of completion. And more information about the certificate after 2 months, if you haven't received it, you can contact Marina Martins. Her email address is here. So this is more about what is required for you to get the certificate. With that, we'll start with today's session. We'll have a brief introduction about ARSET program itself. Then we will talk about tropical storms, just a little bit of definitions that we use throughout this webinar series, and then we'll talk about tropical storm impacts, which is really what we want to know, how remote sensing can be used, and then can be used for decision making. We will also have a review of pre-storm emergency preparedness, monitor approaching storms with NASA remote sensing and Earth system model data and tools. And not only that, we will talk about data sets themselves, but we will have some demonstrations, live demonstrations of some tools that you can use to access these data. And finally, we will have an exercise for you to do. It's a monitor a storm exercise that at the end of this session, we will be still online. You can go through the exercise, and then we will have a question answer session based on that. So this gives you opportunity to work with some of the tools and look at some of the data so that we can have better discussion at the end of this webinar. And by the way, I wanted to mention that this session itself is 2 hours long, so we have enough time to explore all the tools and data and then talk about them later on. Okay, so we'll start with information about ARSET itself, and some of you may have taken ARSET webinars before, so you already know. But those of you who are new, NASA's Applied Remote Sensing Training Program is supported by NASA Applied Sciences, and the mission is to empower the global community through remote sensing training. As shown here, we have 4 different themes in which ARSET does training: so water resources, disasters, land and air quality. There are about 15 NASA scientists at different centers working in ARSET. There's a number of students and other helpers who support ARSET webinar and ARSET program. The target audience for us is policymakers and environmental professionals. So the idea here is that NASA has a large number of data sets which help in many ways for water resources management, disasters management, land and air quality management. So how can these be used for decision making? That is what ARSET's goal is. That's what we're trying to do these webinars for. There are different types of trainings. So the formats are, we have online training such as this. They are live or recorded sessions. They are 4 to 6 hours in length. They vary depending on the topic. Advanced trainings, they include some image processing or hands-on training. In here, though this is the one that we're doing today, it's more or less an introductory webinar, you will have a chance to explore some of the data sets online using tools. Next type of training we do is in-person training. This can vary in length from 2 to 7 days, again depending on the topic. And they are usually held in a computer lab, and it's a mix of presentations as well as hands-on exercises on computer. And it's focused regionally and also thematically. And participants are very actively doing case studies in in-person trainings. Then lastly, we have train the trainers. So there are online training manuals or for best practices manuals for doing webinars. If you are a trainer and if you want to do training for your organizations or other people you're working with, your clients or other stakeholders, then ARSET helps you to do how to do the training, how to put the material together, what is the best way to communicate. And for that, there is a manual online, and there is also a webinar that you can view online to see Train the Trainer series. This is the ARSET website. This is the source of all the information. Past webinars are found here too. You can look at online trainings or in-person trainings. You will see that the presentations are there as well as recordings are there whenever possible, and they are free to all. You can view them at your convenience. There is a lot of information on the website, so we request you to go through the website and explore, and you will find what you need perhaps. Also, there is a listserv, ARSET listserv. If you are not part of this, then we request that you join ARSET listserv. This is your way to stay in touch with ARSET activities. Whenever there are new trainings coming up, the announcements are sent out. If there are our newsletter sometimes is sent through, there is always notifications if there's something new on the website. So there are not too many emails sent, but if you're part of the listserv, then you do stay in touch with ARSET activities and join when you think it's appropriate for you. So now we're going to start talking about tropical storms. And this is just overall information about tropical storms and the definitions and words that we will be using today and next week. So what are tropical storms? So these are low pressure systems and they form over warm tropical oceans. The origin of all tropical storms is on oceans, and usually it is when there are warmer temperatures, and research has shown that greater than 26.5 degrees Celsius is some kind of threshold when a lot of convection starts and then storm starts forming over warm oceans. Usually after forming over the ocean, storm moves along the and it goes near the coastline and over land. It is typically, you see a circular eye in between, as you can see in here. This is Hurricane Harvey, last year formed in the Gulf of Mexico and did landfall in Texas. So you can see clear circular eye here, where you have a very strong sustained wind in the eye wall region. Usually eye itself is clear, but you do see these spirals of clouds and rain, and they extend hundreds of kilometers from the storm center itself. So sustained wind, as mentioned here, could be larger than 60 kilometers per hour. And depending on the size and intensity, it varies. So that's just basic defining tropical storms. Also to keep in mind here is that they're known by different names, different regions. In Atlantic Ocean and also in Northeast Pacific Ocean, it's known as hurricanes. So in the US, we always talk about hurricanes. If you're in Indian Ocean region, they're referred to as cyclones or tropical cyclones. And in Northwest Pacific Ocean, they're referred to as typhoons. But they basically mean the same thing. They are tropical storms originating over warm oceans and then moving along the winds and with the winds, and they go on the nearby continents, and they have a lot of disasters associated with them because of heavy winds and rainfall. So with this, it's also important to know that technically there are different types of storms than mid-latitude storms. Here in mid-latitude in the US, we always have weather fronts coming, and they also bring damaging rain and wind sometimes, but tropical storms are not the same. They're very different dynamically. Physical processes are different, and so when these are specific types of storms, they form mostly in tropics, and that is shown here. So as you see here, this is from World Meteorological Organization. The red regions, they are the regions where tropical storms form. And the seasons vary with which region you're in. Hurricane season here in the US is from June to November, and typhoon seasons in May to November. Cyclones in South Pacific and Australia are November to April. In Indian Ocean, here in region 4, there are 2 seasons related to monsoon winds moving in and out, so April to June and September to November. And then again, cyclone season along east coast of Africa, this is this region, it's November to April. So slight variations depending on the seasonality in that area, but these are the areas where tropical storms are found. So in the chat box, can you indicate the country you are from? Are you from any of the countries which experience tropical storms? So if so, please go to the chat box and enter your answer, and we'll just take a pause for 30 seconds while you type the answers. Okay, so moving on forward, in the same region that we saw, these are the tropical storm frequency and tracks. This is from NOVA, and what you see here is intensity of the storms. So the strongest storms are in red and pink and purple, and you can see here where strong intense storms form. On the left-hand side, you can see frequency time series, and this goes from 1995 to 2010, and then these are frequencies from a particular document here, given here. This is global. What you can see is that usually about 70 to 80 forms storms form every year, at least during this time period. This is Northern Hemisphere, this is Southern Hemisphere, and then this is by ocean basin, so Atlantic, North Pacific, Western North Pacific. And what you see here is that each basin here, say North Atlantic compared to say South Pacific, you do see interannual variability. This is Southern Indian Ocean. You do see variability from year to year. So it is not always easy to predict how many storms will form in which ocean basins, but that's basically the global picture that you get in last several years. To notice here is that these are the regions where this is the typhoon region and this is the hurricane region. Here is where you have very intense storms forming. Sorry. Okay. So usually you must have heard tropical cyclone have names. Hurricane Harvey, Hurricane Irma, or Typhoon Noru. So these are all different names. And if you go to this website, World Meteorological Organization, it describes how the names are formed and the entire history of how it came about. But basically, WMO maintains a rotating list of cyclone. Usually every 6 years, names can be repeated. And here's just a sample shown for Caribbean Sea and Gulf of Mexico. Different names are given for different years. They can be rotated after 6 years. For the US, National Hurricane Center, NOAA's National Hurricane Center, it compiles names of hurricanes, and WMO uses that. Cyclone names are given alphabetically, and they're altered female and male names. Starting from a female name, as you can see, it's Arlene, Brad, Cindy, Dawn. So they're male and female names alphabetically given throughout the season. Some names are retired, and there is a lot of information on, again, WMO, such as Hurricane Katrina. There are some major storms. Those names are not used again. They are just reserved for special case. So there are some names which you don't see again and again. A few, but there are some. Okay. So most important to remember now is tropical cyclone intensity, how it is decided. So as you can see, if you are from the tropical storm area, when you either read news or hear news, you would see there's a tropical depression forming, or there's a tropical storm forming, hurricane or typhoon, or there's a major hurricane or super typhoon forming. How are they decided? So they are based on their wind intensity. As you can see, tropical depression, it's a cyclone with maximum sustained winds for about 38 miles per hour or 61 kilometers per hour, or it's less than that. Tropical storm is slightly more intense with about 62 to 117 kilometers per hour winds. Hurricane and typhoon, they are even stronger. These are the fully matured storms with very high winds, 119 to 20 kilometers per hour or even higher. There could be gust winds which are higher than that too. And in the Western Pacific Ocean, the hurricanes which are called typhoons, they are very similarly defined storms. And so major hurricanes or super typhoons, they have winds greater than 178 kilometers. Sometimes typhoons above 150 kilometers per hour also is defined as super typhoon. So these are the basic categories that you will see based on wind speed associated with the storm. And so once you have a hurricane formed, then there are multiple categories. And this comes from a Saffir-Simpson wind scale, and you can read more about this from NOAA's National Hurricane Center. There is a document that describes how it is formed. And so category 1 hurricane is 119 to 153 kilometers per hour, and you move down, and category 5 hurricane, which is the strongest, is greater than 250 kilometers per hour winds. So these are all major hurricanes, and again they are also defined by Saffir-Simpson wind scale, and that also comes, as you can read from this site, is that depending on how much damage these winds cause, based on that the hurricane categories are defined, and it is true for all cyclones and typhoons as well. So here is what to note here. WMO provides information about the regional centers where hurricane or tropical cyclone information can be found. There are portals where you can go to. Here in the US, National Hurricane Center from NOAA is the main center that provides information about hurricane outlook, hurricane forecast. So this is the site to go to, and all the regions where storms formed are shown here, and numbered 1 to all the way to 8. And what you see here is, depending on which region you are in, based on these numbers, you can go to any of these sites listed here. Again, this is from WMO information. You can see Hurricane Center here in the US. There is also a Central Pacific Hurricane Center that provides information about hurricanes and storms forming in this region, in the Pacific region. Then Japan Meteorological Agency, India Meteorological Department, this is Meteo France, and then a bunch of Australian organizations, so Bureau of Meteorology and Bureau of Meteorology in different places, different cities forming here. Storms forming here are monitored by them, and South Pacific again are from NADI and from New Zealand, Wellington. So these are all the sites. If the storms are forming already, these are the sites which have dedicated information about origin and track and intensity and monitoring. So this is operational data that you can see when a storm forms. So what we want to switch now is to tropical storm impacts. We saw about different categories, different wind speeds associated with that. So for any emergency preparedness, it is important to know what to expect, and some of that has been, a lot of has been researched, and some examples are shown here. So here is some information about cyclone impacts. This is based on data from 1980 to 2009, and what you see here are different regions. They're color-coded, they're defined by World Health Organization, and is African, Americas, Europe, Eastern Mediterranean, Southeast Asia, and Western Pacific, and they are color-coded. And on top, what you see is frequency by region, frequency of storms, how many formed, deaths, number of deaths occurred in each region, and then overall affected population by these storms. And the numbers are given here, total numbers are given here. What is interesting to see here is that it is the regions of Americas which have 37% storms forming, and Western Pacific region has 45% of storms forming. So what you see here is that it's the Atlantic Ocean, Gulf of Mexico, and Pacific Ocean have most of the storms forming. Everywhere else, such as Southeast Asia and also in African region, there is small frequency of storms forming in these regions. But when you see the deaths, about 80% of deaths occur in Southeast Asia, partly because there is more population in that region and perhaps less preparedness than other countries. Overall population affected also is large in Southeast Asia, and then followed by Gulf of Mexico and Atlantic Ocean as well as Pacific Ocean. So this is where you have major impacts, a lot of population affected and deaths occurring in these regions. So these here is where preparedness strategy they help, and more data or more information you have, better policies can be designed, better decision strategies can be designed. So specifically talking about US, and this is also true in general for all tropical storm regions, is that major cause of damage is shown here. This is 1963 to 2012 data, but that is true, extended after that too. What you see here is that deaths occurred because of storm surge and flooding, coastal flooding because of that. Then intense rain, heavy rainfall inland and flooding caused by storm-related rain, and those, they cause a lot of deaths. So almost most deaths occurring related to tropical cyclones, at least here in the US, they are either because of coastal flooding or inland flooding related to heavy rain. There is also wind damage, surf damage, also because there is offshore assets, they can be damaged by hurricanes, by winds and rain and everything. Tornadoes occur. It's small percentage, but they do occur, and they can also cause deaths and damages. And of course, there are unknown reasons why deaths occurred. Partly people are not evacuated in time, or roads are blocked, or other regions, could be health regions. But basically, what we want to note here is that flooding is the major cause of damage and destruction and deaths for sure, at least here in the US. So when you talk about cyclone impacts, here is basically socioeconomic consequences of cyclones. So the slide we saw just now for the US, it's very difficult to do that for the whole globe because of the data availability. So it's not easy to quantify. But in general, what happens is that there is hazard, such as you have rain and winds and flooding. There is exposure, that is flood-prone area or coastal areas. Larger the area, there is more exposure. And then there is population density, assets exposed in areas, poverty, governance. All these play a role in actual impacts. So as we can see from this diagram, there is very immediate damage and mortality, morbidity, displacement, asset damage. This occurs right as the heavy winds, rain, flooding occur. So these are very immediate impacts. So there is one kind of preparedness needed for that. Then there is short-term and long-term effect. There are indirect losses, and there are loss of well-being. Also, there are damages that needs years to recover from. So again, depending on how strong the force is, which of these factors affect a particular area, depending on that, preparedness is required. So either, in any case, immediate preparedness is always required, but then there are decisions have to be made for recovery or even mitigation to stand against such storms. So most of these storms, not only just deaths and damages occurred, but they are very costly, as this is shown for the US. So this is again from NOAA, and what you can see, number of events, and this is the cost in billions of dollars. So 2017 was one of the strongest years. So this is gray lines here are 5-year mean, and yellow are tropical cyclone numbers, and then this is the gray lighter gray, that is the cost. So this is the cost. This is actually the 5-year mean, and these are the storms. You can clearly see that the economic impact is in billions of dollars. So 2017 alone for the US was about $350 billion damages occurred because of number of very strong hurricanes striking the land region. You can see that there is a strong interannual variability also, so it is difficult to know exactly how many storms will form in each season. So again, in addition to deaths, destructions, other asset damages, it all costs economically as well. And here is something else. It's like how Category 1, which is tropical cyclone, the damages are mostly due to storm surge, like 4 to 5 feet above normal can be there. There are likely damages, and this is for your information. This is again from the past data and experience that people have formed this impact assessment, is that when there is Category 1 storm forming or hurricane forming, there is storm surge, the damages are primarily restricted to trees and shrubberies. If there are unanchored assets, they can fly off. But there's not really a lot of substantial damages to structures unless it is poorly constructed building, or then it gets damaged. But mostly coastal road flooding, minor damages can be expected from Category 1. Category 2, which is stronger winds, has larger storm surge, like 6 to 8 feet above normal. And then damage list also goes up. What you can see here is that coastal roads can have major flooding. There could be, some roads could be cut off. There is considerable damage to piers, and marinas flooded. So a small craft, they need protection. Mooring can be damaged. So some more damage occurs. Even in buildings, there are windows and doors and roofing material can get destroyed because of winds. Category 3, 9 to 12 feet above normal storm surge. And here you really have to start thinking about evacuation from low-lying residents, in addition to all the damages that occur to roofing and windows, trees. There is serious flooding along the coast, and anywhere where storm moves inland, there is flooding starts occurring, and then the low-lying area gets flooded soon. So this is the time when evacuation is recommended. Going to extreme Category 4, there is massive evacuation of inland residences in addition to all other damages. And as you can see, very large storm surge, 13 to 18 feet above normal. So a lot of coastal flooding goes on. And finally, Category 5 is the really catastrophic hurricane. And as you can see, there is a major erosion of the beaches, along with all the flooding, all the destruction, and then very high storm surge. So coastal areas are totally inundated at this time, and a lot of rain and wind damages occur to property, to woods and trees and shrubs. A lot of catastrophic damages occur at this point. So these are all the impacts defined, and then so preparedness has to be according to how strong the storm is. And so pre-storm, what today we want to talk about is how would you prepare when you know that there is a storm coming. So usually there are ways to do is to plan ahead. And here is FEMA, or Federal Emergency Management Association. They have this website describes how to be hurricane ready. And so main recommendation is that if you are in the areas where a lot of storms occur every year, or even a few storms occur every year, you want to plan ahead. So usually properties and infrastructure which are vulnerable, they need attention. So roads, bridges, they need attention. They need strengthening before the storm season starts. Water control facilities, buildings, utilities, other public and private properties. So basically preparedness before the storm is really a long-term, in a like year or 2 years before, or it's a sustained way of maintaining properties, roads, bridges in such a way that it can withstand different categories of storms. And then, so the idea here is that reduce excessive losses just by taking mitigation before even the storms start occurring. So before the storm season starts, think of how to protect against storm surge, high winds or torrential rain and flooding. So these are the factors that one needs to worry about preparedness. So tropical cyclone preparedness, so planning ahead, that means the plan has to be in place so you have to know the conditions when the plan comes into action. So that depends on data or past experiences. Also, what has to be decided is sequence of decisions to make or chain of command, what to do after what, emergency functions and who will perform what. So this could be at organizational level or even at household level. It has to be decided ahead of time. Specific evacuation procedure, routes, exit plans, these have to be thought out before even the storm season starts. Procedures for accounting for personnel, equipment, so these are some of the things to keep in mind. So can remote sensing help? And this is what we want to see from now onwards. These are the conditions we want to know for planning. Now, what we talked about here was to plan or for mitigation or prepare ahead of time. Once you know that tropical storm is already formed or depression is formed, and it might be moving into your area, so almost about 24 to 48 hours before, your immediate preparedness changes a little bit. It's not just, you have already done mitigation based on data. Here now, you already have a storm that originated. So what needs to be done is monitor this storm. Where is it moving? So of course, you start with your local news and weather reports, but can remote sensing help? That's what we want to see next. You prepare for evacuation, testing your emergency communication plans. Again, these are all recommended by FEMA. You also have your emergency supplies ready that you want to go with, some important papers such as insurance policies, other financial documents that you may want to just take with you if you have to evacuate. If you are planning to stay where you are, then you want to stock emergency supplies. So this is more like immediate preparedness before even storm comes to your area, but it has already started. Maybe it will be there in 48 hours or 24 hours. And then finally, you want to see all kinds of emergency contingency you want to make decisions about. So we talked so far about preparedness for tropical storms. We talked about planning mitigation and then planning for upcoming storm in, say, next 24 to 48 hours. So what kind of data would we need to prepare for these storms? And it's listed here, as you can see, for planning mitigation. So this is long-term plan, preparedness a year ahead or 2 years ahead. You need historical or climatological data of storm frequency, tracks, sea level pressure, size and wind speed in your area, also precipitation, flood extent, storm surge, coastal flooding, As many cases as you can see from past, and if you have damage and destruction data for those storms, you can plan for mitigation in particular areas or where they're more vulnerable to flooding or winds or precipitation, etc. When a storm is already formed and if you see it's approaching in your area, then you need near real-time data, and also you need forecast data to prepare for the storm. Again, you need the same information. You want to know which direction the storm is going to go, where it's going to make landfall, how strong the winds will be, how much precipitation is forecasted, and where flooding might occur. Storm surge, of course, is a major cause of coastal flooding. Can you have forecast or near real-time data for that? So these are the data that are needed. In addition, there are other data sets which help prepare for emergencies, such as terrain. If you are in low-lying area, there is more chance of flooding. Population and infrastructure information helps where more relief operations are needed or where emergency preparedness is more important, more people are affected. So if there are a lot of people in low-lying area, then that's where emergency preparedness has to occur first. And if evacuation has to be planned, it's that area that gets priority, etc. Other damage and destruction in situ information, as I mentioned, of course, are very important for historical data. Based on that, strategies can be devised. So most of these data, historical as well as near real-time and forecast, they are available from NASA remote sensing, and there are Earth system models they provide a forecast that can be used for planning. So in addition, these centers are mentioned here. We talked about them. These are operational centers. They provide information about tropical storms like National Hurricane Center, Central Pacific Hurricane Center, Joint Typhoon Warning Center. Also, there is GDAX, Global Disasters and Alert Coordination System, that provides information about not just tropical storms, but other disasters also. But the focus of today's talk is about NASA remote sensing and Earth system model data. So when you are preparing for storm, your first stop is the operational center. But then you can use these research quality products from NASA that can help you monitor approaching storm. So depending on which region you are, you can visit one of these sites every day and see if there is any storm forming in your area. You would usually see an indication here on the map. Once you see that, you can actually start using NASA data, and that's what we're going to look at next, what data to use. One more thing, National Hurricane Center provides emergency preparedness course, especially for FEMA members. This is Federal Emergency Management Association, and here is the link. You can visit if you like. This training focuses on National Hurricane Center resources. What we are going to look at here for preparedness is how we can use NASA remote sensing data. Okay. And so we'll start with satellites, which help monitor for tropical cyclones. And these are the many satellites that NASA has already in space, but these are most relevant for tropical cyclones monitoring. Tropical Rainfall Measuring Mission. This was a long-flying mission from November 1997 to April 2015. So this satellite is no longer flying, but these data are very useful because they provide history of precipitation related to tropical storms. And as the name suggests, it focuses on tropics. So it provides information about tropical rainfall associated with storms. And so it's very important data, satellite to keep in mind. A follow-up mission to TRMM is Global Precipitation Measurement Mission, or GPM, which was launched in February of 2014 and continues to provide high-quality precipitation measurements. So for near real-time, GPM data are very useful to monitor an approaching storm. Terra and Aqua, these two are long-flying satellites, and they provide information. We are going to talk about specific sensor, MODIS, and that sensor provides information about land surface, about reflectance from cloud top, so that you can see imagery and you can track storms by looking at the images. Also, there is SUMI National Polar Orbiting Partnership, or SNPP satellite, which is a NASA-NOAA partnership that was launched in 2011. This continues what MODIS started years ago, and this satellite, we will talk about a sensor VIRS that provides information and you can use to track storm. So at this point, I just want to take a couple of seconds just to go to ARSET website and show you this session 2B in the Fundamentals of Remote Sensing session. If you have not already seen this, here is where you will find all the information about the satellites and sensors that we will be talking about today. So these are the sensors flying on satellites we just talked about. TRIM and GPM, they both have microwave imager as well as radar. TRIM had single frequency precipitation radar in Ku band, and GPM has dual frequency precipitation radar. And they provide not only information of rainfall at surface, but also how precipitation particles are distributed in vertical. And so when there is a storm occurring, precipitation in the atmosphere provides a lot of latent heating or heating to the storm and helps intensify sometimes. So these satellites also provide this research quality product that can help in understanding how tropical storm intensity, how it changes with its life cycle. Terra and Aqua MODIS, which is moderate resolution imaging spectroradiometer, that also is a widely used versatile instrument, and that provides deflectance from clouds or land surface or ocean surface. And so images are very useful in tracking storms. So when a storm already has originated, one can, an approaching storm can be monitored using imagery. Same with SNPP VIRS, has the same imaging capability with visible and infrared spectrum, and there is additional channel in VIRS that is day-night imagery. So at nighttime, low emission data are also received by VIRS, and they can help in tracking lights on the surface. So when there is power outage, this band can help in monitoring impact of storm or disasters on power outages. So we're just going to briefly go over all the satellites we talked about. However, as I said, more information can be found on ARSET website in the Fundamentals of Remote Sensing session. So GPM, which is a low Earth orbiting satellite like TRIM was, the difference is that TRIM focused just on tropics, whereas GPM coverage is extended from 65 south to 65 north. And there is a revisit time over land with a number of constellation satellites. We'll talk about that next. Is a few hours over land, so it has a good coverage. And as we talked, these are the sensors for GPM. Important thing to notice here is these constellation satellites. And so there always have been satellites flying from NASA, from NOAA, and from other international agencies. So both TRIM and GPM, they use information from these national, international satellites and combine with TRIM and GPM sensor information to provide a better coverage, both in space and time, to get precipitation data. And so there are two multi-satellite algorithms. They derive precipitation from TRIM and GPM, and you can find more information at this website. So TRIM multi-satellite precipitation analysis, TMPA, which has been around for many years, since 1997, it's widely used for many applications, including flood monitoring and iMerge, which is the integrated multi-satellite retrievals for GPM. It is similar to TMPA in the sense that uses constellation information, satellite information with GPM. And so these are the constellation satellites currently in space for GPM. TRIM, of course, is no longer there, but you can see that there are many satellites from some from NASA, some NOAA, Japanese Space Agency, French and Indian Space Agency in European Union. All these satellites listed here, they have microwave imagers or radiometers on them, and so data from GPM core satellite, microwave imager and dual precipitation radar, they're used to calibrate all these combined microwave data and come up with integrated rainfall measurements. Not only that, final product is also calibrated with rain gauge over length to get as accurate precipitation as one can get, and you can get more information from all the websites given here. And so iMerge is the product to use when you want to monitor an approaching storm. There are multiple products, early, late, and final, and as you can see, they have different latency. That is a 5-hour latency for near real-time or early data, but these are the one which should be used for monitoring storm that is upcoming or already formed. You can start looking at early data. And if you go to a website that provides precipitation measurement mission information, you will see iMerge data for last half hour available here. And so this is also one way to keep tracking how precipitation is evolving associated with a storm. So this is iMerge that we will be looking at later, how to access that. Just to give a comparison between TMPA and iMerge. So TRIM, which is no longer available, but it's very important for climatological perspective. And so TRIM calibration is right now used with other constellation satellites, and TMPA continues to be available, although TRIM is not there. TRIM calibration, TRIM instrument calibration is used to calibrate other constellation satellites, and you can get TMPA at 1/4 degree resolution. iMerge, on the other hand, has higher resolution. It's 1/10 of a degree. Special coverage, of course, is we are focusing here on tropics, so they both provide tropical coverage very nicely. TMPA has 3-hour temporal resolution, whereas iMerge is available every half hour, very convenient in monitoring storm, as we will see later in a demo. There is temporal coverage here, that, as we talked about, and TMPA has already been used for many applications, especially for monitoring storms and flooding. But iMerge also is continuing, and so now the plan is that there will be a combined product available that combines TMP and iMerge, so that a long precipitation data will be available starting from 1998 to present. All data will be at 1/10 degree resolution and will also have half-hourly temporal resolution. So then all the applications can use that data. And here is the website where you can quickly access data. There is also an online training that helps you, the guides through all the products available and how to access them. So this is the this is another way to get this precipitation data and analyze it online. We will see a short demo at the end. This is the NASA Giovanni site that provides search by keyword. You can search iMerge here. You can provide special and temporal subsetting here, and then have different analysis. You can have maps or have time series, or you can have miscellaneous, such as you can have histogram or scatter plot. And so this is, without downloading, you can quickly look at the data. We'll see this demo later, but keep in mind that this is a site to go to have a quick look at the data. And this is the tropical cyclone portal that GPM has. Anytime, and then again, we can go back and see this. Not only it has last half-hourly data, it has extreme weather news. Any new storm forms, it also has information. When you go to tropical applications, you can go to tropical cyclones. Whenever there is a storm forming, it always has information and precipitation associated with it. And as you can see, not just surface rainfall, but also has vertical information that shows it is related to strength of a storm. So this also is a useful portal to quickly look at rainfall associated with GPM. Two satellites we talked about, Terra and Aqua. These are both polar orbiting satellites, provide information at 10:30 a.m. and p.m. for Terra and 1:30 a.m. and p.m. for Aqua. So any region has the same local time of observations. So twice daily observations are available from these satellites. And they are long-term satellite flying from 1999 to 2002. That's for Aqua. They are continuing. So the sensor that we are going to talk about for monitoring storm is MODIS. There are many spectral bands, 36, ranging from visible to near infrared to middle infrared. And they all help look at different parts of the atmosphere and surface. Depending on the spectral band, the resolution can vary from 250 meter, 500 meter, and 1 kilometer. And the images that we're going to look at will be high-resolution images for monitoring storm. They also have daily data available, also composite at different time scale, but we can look at daily data to see an approaching storm. These data can be found from LPDAC, or Land Processing Distributed Archive Center. You can download raw data from here. We will look at this data later on using a web tool. Similarly, SUMI NPP is also a polar orbiting satellite in 1:30 a.m. p.m. equator crossing time. So local time of observation would be 1:30 a.m. p.m. And the instrument we are going to talk about is VIRS, that is Visible Infrared Imaging Radiometer Suite. Again, the resolution here is 375 to 750 meters, depending on which band you are in, but basically the same spectral bands as MODIS are available. That's visible IR, near IR. In addition, as we talked about earlier, there is a day-night band. And an example is shown here. This is over Spain. At night, you can see where the lights are on the surface, and that gives you indication of urban areas on the ground at nighttime. So if there is a disaster and there is power outage, by comparing this imagery during or after or before disasters, you can quickly see where there can be power outage or electricity is lost. This just shows an example of Hurricane Harvey images from MODIS and VIRS. This is on 25th of August as Harvey made landfall over Texas. You can see the clouds. This is the imagery that represents, that can be seen from Terra MODIS. And at the same time, you can see VIRS images at nighttime. It shows where hurricane is, clouds are obscuring surface, but outside you can see where all the lights are. So this imagery, used either separately or together, provide a lot of information about an approaching storm. There is also a site that National Hurricane Center maintains, and this is all about geostationary satellite. There are a number of geostationary satellites covering different parts of Earth. These satellites, they're always looking at the same disk, and they go around with Earth. So there is a constant observing platform available. For the Atlantic and Pacific Oceans, there are 2 satellites that goes east and west. The multiple series of satellites that have been launched over the years. And then Meteosat covers Asia as well as part of Indian Ocean and part of east coast of Africa. Himawari is a Japanese satellite that covers Pacific Ocean. So for continuous coverage or near real-time coverage of storm, one can see these site, and I just want to quickly show that if once a storm emerges, this latest satellite images can loop and show through. So this is GOES images, and you can either look at visible, which just shows images of reflected sunlight, or you can look at IR, which shows how cold cloud tops are, or how much moisture there is. So these are different, but you can quickly look at the visible image. This is for the Atlantic Ocean, and it will show you every 15 minutes. It shows how things are changing. So as different image comes in, you can monitor these clouds, and you can. There is also a tropical cyclone floater. So any of these basins, if there is a tropical cyclone going on, you have images available. We're just going to quickly look at this Fakir, which formed in the southern Indian Ocean. This imagery comes from Meteosat, and then it shows the latest image based on satellites. So these regions show where there is precipitation or weather going on. So this is a quick way of looking at near real-time satellite images from different geostationary satellites also. Next, we want to talk about NASA Earth System model. This model that we're going to talk about is called Earth Observing System, or GEOS version 5. That provides near real-time data as well as forecast data for up to 10 days. Data resolution is here about 5/16 to 1/4 degree latitude and longitude and latitude grids. And this is just the detail that it contains ocean, atmosphere, general circulation, as well as chemistry in the model. And this is an example of 2012 Hurricane Isaac that moved over the US, and this is tracked by using GEOS 5 forecast data. So in addition to remote sensing data that we talked about from GPM, Terra, Aqua, SNPB, GEOS 5 also provides very important information. More importantly, GEOS 5 includes some of the satellite data they are assimilated in there. That information is used in the model itself. So that way, it provides a nice way to look at a number of parameters which you would like to see if a storm has already started over the ocean basin near your area. And so this is the website where you can visually see some of the maps. You can see that number of variables are there. Precipitation and sea level pressure, of course, is very useful because lower the sea level pressure, the stronger or more intense a hurricane or storm would be. Similarly, there is wind speed and direction. This is shown as these wind bars. So direction is here from northwest, as you can see these, and the magnitude of wind speed can be figured out from these bars here. If it is 1, it is 5 knots, and it's short one, it's 5, longer one, it's 10. And this is just the conventional way of looking at weather maps. So this shows wind speed and direction. Not only that, this is North America, but you can see that there are other regions where you can go and look at initial time and there is forecast time. And just quickly, we can look at this. You can pick any time from a few, like 8th April is the first day available, and then it goes on to the current date. You can look at the current data. So this is 850 hectopascal wind speed, which is close to the surface. This is what you want to monitor if you see a storm approaching. And you can pick any forecast time. So this is like 2 days later, and you can animate how things are going to change. So if you already have a storm, it's actually trying to animate the data. If you have a storm already formed somewhere where the ocean, looking at the forecast loop helps you see how storm is propagating or what the approximate track is going to be. Is it going to landfall in your area? So you can do this every hour actually. So this shows forecast. And if you have a storm somewhere, you will see that. So this is a useful site to look at a near real-time data as well as forecast. In addition, we talked about data that can help in strategizing emergency planning and preparedness. That one of them is terrain data. And that also is available from NASA remote sensing mission. There was a shuttle radar topography mission, or SRTM, that flew on Space Shuttle Endeavour. This was in 2000. But it provided coverage of entire Earth. And SRTM is a radar that looks at backscattered data. And so looking at transmitted and received radar waves, topography is derived. And so from SRTM, data are available at 30-meter resolution globally. So that helps in deciding where there are low-lying areas are. You can use SRTM data just to look at the topography, or you can use it with GIS, look at slope and flow direction, also area based on this elevation data. And here is a link to an ARSET webinar that you can see for more details how to work with SRTM data, how to get them, and how to process them using GIS platform. This helps if a storm is approaching. You already know which areas are in danger of getting flooded or getting more affected. So this is a site where you can get SRTM elevation data. This is a GTAX USGS site. You can define your region of interest, and then you can have multiple choices here. NASA SRTM 30-meter resolution data are available here that then you can download. Additionally, there is a CDAC, or Socioeconomic Data and Application Center, that NASA has data about population density that shown here. These data are visually available. You can quickly see it on this website, or you can download this data as geotiffs and then work with GIS in your region. So this also helps in deciding, if approaching storm, which area or where the largest population is going to be under influence of this storm. So there are also other useful data listed here available from CDAC. There is urban data, where there is urban and suburban areas. They are demarcated using satellite, Landsat satellite data. Global reservoir and dams are available. If the storm is approaching, maybe these are the regions they need attention. for management. There is low elevation coastal zones, global roads, energy infrastructure, and agricultural land. All these layers are available from CDAC. So in addition to satellite data and images, we have GEOS near real-time and forecast data. We have ancillary data such as terrain data and socioeconomic data. So they all can help in preparing for a storm. This brings us to a Global Disaster Alert and Coordination System site. This is a site that is maintained by European Union, and you can see that it provides near real-time and past storm data. There are other disasters also, but data and maps are available. In addition, media reports, impacts, they are all reported on this site. This site also includes some of the NASA images from TRIM-GPM and MODIS. And so this is a good site. As soon as a storm forms, this provides information. And I just want to show you the site itself because it can provide a lot of information. Once you go to the site, the latest news are always available. You can register to get information in real time on your phone app also. Information is there for other disasters, but we are interested in tropical cyclones here. So as soon as a cyclone forms, you can see it on the map and you can click on this cyclone itself, and then you get event summary. What was the date, what are the countries affected, population exposed, maximum wind speed. So these information are available, and then we will see next week in detail how some of the maps and resources can be used to look at storm surge and other information. So that we are going to cover next week, but this is a good site to keep in mind. If you already know a storm is forming nearby in your region, you can start tracking using these multiple resources. So this brings us to a demonstration. So what we talked about initially was all the tropical storm, how we define, how the intensity is defined, what are the impacts, how to mitigate or plan for them, and how remote sensing and modeling data can help in preparing for them. So now we're going to look at two specific web tools, NASA Worldview and Giovanni. These two tools help in looking at data we just talked about. And what we're going to look at is Hurricane Harvey, which formed in Atlantic Ocean and Gulf of Mexico in August, September of 2017, and a recent cyclone Marcus that formed in southern Indian Ocean near the coast of Australia. That was in last month actually. So Harvey, of course, it was impact was very much. 30,000 people were displaced from Houston area, and it cost about $190 billion. There was power outages following this storm, and so this is one storm that we're going to look at. And the second one is Tropical Cyclone Marcus. It affected Darwin as it moved southward. If you look at the history of this storm, it intensified later on, but when it hit Darwin, it was Category 2 cyclone, and it affected the city, and there was flooding and power outages. So we are going to look at two short animation to see how these storms can be tracked before they arrive. Okay. However, what to keep in mind is that when this happens in near real time, you will be using the same tools. So this is just for an example to show how storms can be tracked. And so I'm going to start with demonstration. So before you actually go to Worldview or Giovanni, Please note this website, NASA Earth Data website. You will need to register as a user. So by going through this, you can enter your username and password. You can choose. You can provide your profile information, including your email, your country where you are from, affiliation, and selected study area. So data are free, but user registration is required. Once you register to NASA Earth Data, you will be able to download data from WorldView, from Giovanni, also from CDAC, and from GDAX for terrain data. So anywhere you find, or LPDAC, MODIS data, where you need data, you can use this login information to download data. So it is just for registration. Once you register, you can go to NASA WorldView. If you are the first time user, you can take a tour, and we recommend that you do. It provides information about how to navigate, what information are available. We're going to skip the tour and look at some of the features right now. So on the left-hand side on WorldView, you can see layer information. You can add layers as well. The one that is showing is MODIS true color imagery. And you can turn off and on by clicking on that eye over here. So true color imagery is red, green, and blue bands, visible bands. They're combined to form an image that looks like you see from your eye. So you can see ocean, you can see clouds, you can see land area in this region. And so you can turn that off for now and look at the coastline and borders and roads. You can place labels, turn on, and then you can see the bars over there. You can share the map you create. You can switch projection, different view. You can take a snapshot of what you have on your screen as either a JPG or PNG image. You can pick any area and make a image and then download that image for later view. These are the options. You can have KMZ that can work with Google Earth. Okay. So what we are going to do is move to the Gulf of Mexico region where Hurricane Harvey formed, and it's easy to pan the map just using the arrow and your mouse. Here's the timeline. You can change years. We'll go to 2017 and month of August when Harvey formed. And then there is date that you can change by using the arrows here or even here. So we'll start from 20th of August. Now you can turn on this MODIS true color imagery, which shows clouds. Here you can see formation of Harvey just beginning. And then when you go through different days, this is 21st, 22nd, 23rd, it's forming now, but you can see that there is orbit gap. You can see the swaths that MODIS covers, but there is usually a gap that sometimes is there. But as you go next day, you can see the hurricane is showing, and on 25th, it made the landfall. 26th and 27th, you can see the movement of the hurricane. So this allows you to track storm out from the ocean all the way when it makes landfall. You can look at Aqua satellite also. This is similar but at different time of day. You can look at SNPP VIRS. So for this particular day, 27th, you have orbit gap right over the Gulf of Mexico. But if you move a day or two, you can see the landfall of storm on 25th, very nicely covered by waves. You can move these layers up and down to bring one on top and bottom. And so this true color imagery allows you to look at storms moving. Now we can have addition, we can say GPM, which is a precipitation satellite. You can see that there are rain rate available from GPM micro imager. And you can click those layers. There are orbit ascending and descending. And this is 25th of August. You can see rainfall from GPM GMI in millimeter per hour. You can see this ascending and descending orbits. So this, depending on the orbit, you can see part of the hurricane or you can see the entire hurricane as shown here. So if you go through different days, you might not see the entire hurricane because of the gaps between the orbits, but there are days when you will see the entire hurricane. So this is just going back through when it originated. You can see part of the storm, but as you move forward, eventually both the orbits show the coverage. So this is how you can view different layers to track storm, look at precipitation associated with it. And when you have two layers combined, you can see the clouds underneath and precipitation on top of it. You can share this image. You can just copy the link and either email or post on social media. You can take a picture of this box, save it as PNG or GeoTIFF for later use. You can pick any area and then download that region and save that for using with other parameters or using in GIS. And this is just showing, saving on your computer the image that you can view later. Okay. So this is how you would navigate through days and different layers to get the best possible view of an approaching storm and get some idea of where it's heading. This is just a quick example of Cyclone Marcus. We are going to do the same thing, look at different layers where storm occurred. Now, when there's a near real storm occurring, WorldView provides data in near real time. So you would do exactly the same. You would find the location of origin from the operational hurricane centers or typhoon warning centers, or all the websites that WMO provides from, say, Japan, from India, from France. Different meteorological agencies provide information about emerging storm when they start. You can start with that information, then go to WorldView and start monitoring data. So this is now 17th of March of this year, and as you can see, true color imagery shows how the storm moved from, say, 16th of March. Then 17th is when it made landfall, and then this is 18th, and then it moved out on the ocean and then got strengthened. But while it was on land, you can see any of these satellites that provide good view of where the storm is. And you can just navigate through this to see the exact movement. You can even see individual bands if you zoom in and look at carefully. You can just add GMI precipitation to it, just like we did for Harvey, and it shows how rainfall is distributed in the storm system as it approaches which area will get more rain. You can interpolate that qualitatively using these images. So important thing to note here is that this allows a quick view and downloading of the data. You also see here that when you are looking at precipitation, there are a lot of orbital gaps. And so because of that, what we want to do is look at Giovanni. which allows us to look at iMerge, which is not just GMI, but combines constellation satellite information and provides half-hourly coverage at 1/10 of a degree. So we're going to look at iMerge data using Giovanni. This is the Giovanni webpage, and this shows how to look at data without orbital gaps, and that's our Giovanni has many other parameters as shown here, but we are going to focus on precipitation, especially related to Harvey and Marcus. Since these are old storms, we're going to look at iMerge Final, which is a research quality product in which rain gauge data are also assimilated. But iMerge early data you would use if no final data or late data are available. In near real time, it's the early data that you'll be using. So for Harvey, we're picking final product. iMerge Final has daily data, has half-hourly data, and there are other parameters like monthly data, and there are error estimation also. We're going to pick daily accumulated precipitation here. And you can see the units are in millimeter here. Once you choose the parameter, it also shows the coverage, the resolution. You can pick the dates. So if it's a near real time, you would pick the most recent date. In this case, for Harvey, we are picking August of 2017, and we will look at the loop through some of the images, daily precipitation images from iMerge. And you can pick by drawing a box in the region of your interest. In this case, it is Gulf of Mexico and Texas, where Harvey made landfall. So here's the box. But you can also go to this icon and pick different shape files for different countries, states, river basins, etc. Or simply draw a box. You have options of animation, you can have time averaged map, you can have two different maps differences. We're going to look at animation because we are interested in tracking or monitoring a storm before it approaches. How much rainfall is associated with it is the indication comes from this data. Once you, or you can have accumulated map too, but we're going to look at animation. Once you pick the options, you can plot data. It takes a few minutes to get the animation going. And here's the animation that you can see. This is Gulf of Mexico and Texas region here. And this is day 20th of August. You can change the speed of the animation. You can have different range. I have changed it to 5 millimeters to 250 millimeters range, and you can decide the color scheme and make the customizer animation. And then you can see the storm moving in. You can go one frame at a time from, and as you can see around 23rd, now it appears in good form. A strong hurricane occurred and then it moved in, and the rainfall as it landfalls, you can see how it increases. This is 27th of August. So this provides you information. What to notice here is that compared to GMI, there are no orbit gaps here because it uses information from other satellites also. So you have a nice continuous spatial coverage. Once you know the storm is very near, you can even just look at half-hourly data. And this is just showing an example of using half-hourly data to see every half hour how precipitation systems moving closer to where you are. And here I've picked 25th of August because that's the day when it came ashore near on the shore of Texas. So once you do 25th of August half-hourly data, you can see animation of this hurricane starting from 00 GMT, and then it's moving. Now, every half hour, you can see rainfall moving, how it comes across. You can even see these different spirals or different bands as they come in. And so this provides fine-scale information like every half hour. You can zoom in to about 1/10 of a degree pixel level here. You can even pick your box at very small region if you're interested and look at animation or look at time series to see how rainfall is changing. And so again, this is just, you can zoom in and keep looking at the animation to see where exactly the maximum impact might be or how rainfall is distributed high or low in different regions. So this allows you to look at precipitation. So next week, when we talk about storm that is already during the storm effect, we want to, that's when we will see how storm surge and wind speed, we will see that. Today, the idea was to introduce Worldview and Giovanni, how you can start monitoring a storm that has initiated over an ocean basin and it's moving to the region of your interest. So with that, we will go back to the presentation. Okay, hello everyone. So you will see that there is a short exercise that you can do right now. You will find that in the handout section if you want to download. But basically we are going to use Worldview to monitor a recent tropical cyclone. And so major objective of this exercise is to give you information or just flavor of how to navigate through some of these tools. You can look at the operational tools like National Hurricane Center, Central Pacific Hurricane Center, Joint Typhoon Warning Center, and GTACs, just to see what the current condition is. And then later on, you can look at Worldview and also look at GEOS file site to see recent storm. So recent cyclone, we're going to look at Cyclone Flamboyant that was formed over southern Indian Ocean. And so I think what we will do is give you a few minutes to work through this exercise. You can start by exploring this operational Hurricane Center websites just to see if you're actually monitoring in near real time, these are the sites you would be watching closer to. If you are in the US area, NHC, if you are in the Pacific Ocean area, CPHC would be the one. For Indian Ocean and Western Pacific Ocean, it's the Typhoon Center that you would be watching every day. As soon as the storm emerges, you can go to GDACs. So you can actually access these sites right now. We'll give you about, it takes about 10 to 15 minutes to go through everything. And then what we will do is we'll come back and have a discussion if you have any questions about these data or tools or any other questions. We can have discussion based on that. Once you go on GDAC's site, you will be able to see this is the storm you are actually trying to see from different data sets. GDEX provides information about, once you click on that, you should be able to see full report of this storm. And this particular storm, we have picked it because it's the most recent one. It's actually offshore, so fortunately it's not affecting any land area. So not many people, the people are not exposed to it, so that is good. But it also provides information about maximum wind speed, was category 1 storm, and maximum storm surge. So it's not affected, and it's not near any land, so it doesn't really affect, but this is the information about the storm itself. So you can take a couple of minutes to go through GDEX and see how to navigate and how to get information. After that, you can go to NASA Worldview. So hopefully everyone has been able to look at GDEX. After that, you can look at this Worldview page. You can turn off all the layers, but just keep the border and place and coastline layer on. Next, you can zoom to the ocean, so it's Southern Indian Ocean, where Flamboyant formed. And then these are the timelines where you can change year, month, and day. So you want to focus on these days, starting from April 17th all the way to May 1st or 2nd. And you can look at Terra Modis, Aqua Modis, and NPP WIRS layers, which shows movement of Flamboyant. Once you go through the exercise, can you please indicate which direction it actually moved after it formed? Next is the GPM page. You can go to the website provided here that shows animation of precipitation in last 7 days. And as you can see, in this area, you can see precipitation associated with Flamboyant. You can see the bands. It starts from a disturbance over here and then it moves and takes form of a tropical storm. This is now 27th of April. Now it starts forming. You can also go to the tropical cyclone page from PMM or GPM applications. Every time you see severe weather or extreme rainfall or storm occurring, you will have information about that event on this page. In the tropical cyclone page, the most recent or current cyclone is usually shown here, as you can see here on the right hand side. And finally, we can look at GEOS 5 weather data from this site. We'll be looking at 850 hectopascal winds, sea level pressure, and precipitation from GEOS 5. You can look at current time. You can also look at forecast. Hopefully, all of you have been able to explore at least most of it or some of the websites and see flamboyant rainfall, clouds, and winds and sea level pressure. And you can take a couple of more minutes to finish some of the steps if you want to. Then we will go back and summarize today's session, and then we will have a question and answer session. Okay, so here is the summary of what we talked today. So for monitoring and preparing for an upcoming storm, you would start with National Weather Service announcement in your area. Look at the local news. In here, if you're in the US, National Hurricane Center. If you are everywhere else, it is either Joint Typhoon Center or Central Pacific Hurricane Center. Once you know that, you can assess the situation in your area in next 2 days to 1 day to next few hours. For that, you have all the data and tools that we talked about. You can keep monitoring MODIS and WIRS imagery. You can look at geostationary images from National Hurricane Center. You can monitor precipitation from GPM and winds and sea level pressure from GEOS 5, especially rain and wind. They help in, if you monitor them, then you know that in next few hours, are you going to have a lot of rain or damaging winds, or what would you want to prepare for? The least you want to stock all the supplies. As FEMA's guideline, once you know the storm is approaching your area, you want to take precautions. Are you in low elevation area? Have you experienced flooding before? Did you have to evacuate before? And should you plan for evacuating in this event? So this is basically how you would prepare for a storm. using some of these remote sensing data and modeling data. So that brings us to the end of today's session. So thank you very much for attending. And then now we want to switch to a question, answer, and discussion session. So here are some of the questions. So you can, there's a question and answer box where you can answer some of these questions. This will help us in learning your experiences with any emergency situation. So the first question is, have you experienced emergency situation due to tropical storm, either winds, rainfall, storm surge, flooding? And if yes, then please indicate the type of emergency that you have experienced. If you have experienced any kind of emergency, so in what capacity did you have to manage that, like individually, or your organization was involved in emergency management? Did you have to plan ahead? If you can give us any indication about that, that would be very helpful for us to learn. Also, have you or your organization used any of the remote sensing data that we talked about today, especially to monitor tropical cyclone or storm? Also, if you can let us know, even if you are using remote sensing data or if you're not using remote sensing data, where do you get the information for emergency management? What's the lead time you require to start preparing for an emergency such as tropical storm? Is it a few hours or a day or two? What kind of information helps you prepare for emergency in what time frame? That also is useful information for us. So now we can address some of your questions. This question answer document that you see here, we will make it available, and discussion answers also, we will make them available to you. Okay. So which methodology do you use to estimate the cost in billions of dollars? So if you go on NOAA or FEMA, so pages, you will find estimates of how they do it. Basically, it's the damage assessment teams, they estimate this. So NASA did not estimate cost in billions, so other agencies help them. In any region, so even there are global organizations such as Red Cross also does that. They all have their assessment teams. They go out where their disasters have occurred, and then they have methodology based on empirical data and models to assess damage in dollars. So what is rip current? And rip current is even when there is, like, when you are on the ocean, you don't see storm surge, but what you see is a rip current. It's the effect of changing pressure at the center of the storm and winds. They create currents which are not part of ocean dynamics. They are just forced by these winds and sea level pressure. They are rip currents. Again, I will give you better definition here. If you go to the NOAA website where they describe rip current. You can see in the chat box there is a site that you can see. So rip current can occur due to any, not just tropical storm, any winds or like the narrow current that can happen. But in this context, it is because of the pressure, low pressure at the center of the storm. Yes, I see the question 3. Please tell us about spatial and temporal pressure code conditions when a cyclone propagates on land. So GIS 5 data would be able to say that. There's a sea level pressure. When you check that, you will be able to see. If you look at the animation loop that we saw, you can see near real-time condition and forecast based on GIS 5 that tells you what the pressure is going to be in your area. So today we mostly saw this visually. You can also download all this data digitally, and some of that we will see next week, right when the storm is in your area. At one location, if you want to monitor all the data, how would you do that? We'll do that next week. Then you can download this data digitally and work with GIS or other tools to do actual analysis. So can we quantify the damage before the storm hits? How far in advance? So that really requires historical data, that in the past, what kind of storm, what intensity, what kind of rainfall structure, precipitation, sea level pressure, size, how did, and in addition to storm data, you also need damage data from the past. And based on that, you can derive empirical or statistical relationship that certain size of storm or certain wind speed that can cause this much damage. But you will not be able to say that just from one storm data. You do need past data to assess that or to determine what kind of impact to expect. So we will have some information about Cygnus constellation next time, which is really experimental product that you get. So I have not seen any wind data from Cygnus that are available online. But I will check and let you know. So what software is available to process and visualize GP and trim data? So if you don't want to use Giovanni can do that. You can spatially and temporally subset your data and visualize it in map forms or time series forms. You can do that. If you want to use other software, you can use GIS. So QGIS is open source GIS, so you can use that. Or so that means you have to download the data and then use with either MATLAB or ITL. These are licensed software. There are R and Python. These are open source software. They all can read trim and GPM data. these data are available in netcdf form or in HDF format. So you can work with any of the softwares to do that. So high resolution elevation data, like 1 to 10 meter data, they're not available globally, regionally based on LiDAR. You can find some of the data that are special data sets. They provide high resolution. And I'm checking whether there is any ester elevation data available at high resolution. So online availability of ester data are also actually 30 meters. Historical world precipitation and temperature data, they are available from multiple sites. Based on remote sensing, for about 20 years, you can find from NASA data. You can go to TRIM is since 1998, and GPM will continue, so you have at least 20 years of data. You can look at Global Precipitation Climatology Project, or GPCP. That is based on remote sensing, and that starts in 1980. So that's a long-term data set. So temperature and precipitation both can be found from reanalysis data. NASA and NOAA, they both have models in which observations are assimilated and then model is used. So reanalysis data from NOAA, from NASA, from European Center, they span multiple years. And you can get reliable data for at least for 1980 onwards. So precipitation temperature can be used from there. There is also, based on surface observations, there is, trying to find the site for you. There's a climate research unit, and that has historical data on land based on both temperature and precipitation. I've just given you the site here. You can find a lot of these data just on land from CRU. So how are these tools able to assist us in predictive analysis? The examples are using a historical model. That is because right now we don't have this current storm, but if you go to this GEOS 5, you will be able to see forecasts. Say for Flamboyant, you can go to GEOS 5 site and see 10-day forecast for that. But these tools you will be able to use exactly the same way in near real time. So for precipitation and from worldview use MODIS and WIRS data, these are only for monitoring in near real time. They are not predictive. They are as you observe in near real time, you see images. But GEOS 5 model does have predictive capability. So there's a how can I look for a specific place in NASA worldview by name or coordinate without the need to zoom in. If you go to NASA worldview, you will be able, once you move your cursor on the screen, you will be able to see the lat lawn and I'm trying to show that to you. But still, you will need to zoom in to actually visually have a good view. Yes, so if you go to World View screen, and when you move your mouse or a cursor on the bottom right, you will see latitude and longitude where you are pointing. But to be able to see things, you will have to zoom in. What are prospects for future storm patterns identification? So this is not a simple question. So what we are basically talking about is short-term forecast from Geosphere that can tell you what's happening now. Future storm pattern is something that requires climate modeling, and that topic is beyond the scope of this webinar. No, we do not have a model to estimate the damages. So here's a question about remote location having less facilities during a cyclone, and that is a real challenge. All this information is available if you have internet access, if you have electricity. And so if you are in a remote location, then the way it works right now in some developing countries or other countries is that government or authority people or NGOs working with disasters management, they would be receiving this information, and then they will be disseminating or somehow providing this information to people in remote locations. But a lot of destruction and damage still goes on because in remote areas or interior areas where people have no way to get information, they have trouble coping with it. They don't have information in time. Yes, so next week we will, this is question 13. One of the biggest problems is with trees and how to best see health of vegetation. Landsat and MODIS, basically Landsat, MODIS has lower resolution, but Landsat data, they do help in looking at vegetation health. A large scale you can also see from MODIS. So next week we'll have an example which shows in color imageries that before and after storm, when trees are damaged or destroyed or they've fallen down, and then how do you monitor them? So there is a way to do it from remote sensing. Yes, so question 14 is one of the answers that I had for earlier questions, is that if you're in remote area, you have no internet, then mobile app is the answer. That's what one should be looking at. For now, I do not have any one app that we can recommend, but we can definitely find out more information on that. And it also depends on where you are in the world, but we can definitely provide that information. I'll look into that. If there are any applications that you can download and use. Oh, this is good. Thank you for informing us. This FEMA has US Hazard US program. So next week, our focus will be on looking at the storm right when it is over land or region of your interest. And as we saw today, it's flooding because of rain and wind damages and everything that affects or impacts the most. So we are also going to look at a flooding pattern resulting from tropical cyclone. So thank you so very much for attending today's session, and we look forward to see you next week when we will, as I said, we'll focus on during and after storm information.